Welcome to today's Explainer. We've got a really fun programming mystery to unravel today. If you're the kind of dev who loves writing clean code, but kind of stresses over execution speed, well, this Explainer is exactly what you need. Today, we're digging into a super fascinating post from a developer named Ang, specifically from Notes-on-Haskell-Programming, Part 203. Ang sets up this brilliant little detective story about code performance. Usually, we assume that writing lower-level, highly manual code means the machine will run it faster, right? But in the Haskell ecosystem, those assumptions are about to get completely flipped. We're going to look at some benchmark results that totally defy common intuition. And by the end of this, you'll walk away with a really actionable understanding of how to write better, faster code.
Okay, let's dive into this. Here is the central question Ang's benchmark throws at us. And honestly, it's a great one. Why on earth do high-level list comprehensions actually beat low-level manual folds when you're running them in the GHC interpreter? Just think about that for a second. A list comprehension is this very high-level, human-readable, beautifully clean way to express what you want to do with your data. A manual fold, on the other hand, especially using something like fold-L, is way closer to the metal. You're manually telling the program exactly how to accumulate those values step by agonizing step. Conventionally, we totally expect the gritty manual approach to win because, well, it supposedly cuts out the middleman, right? But Ang's benchmarks show the exact opposite happening in the interpreter. The elegant list comprehension actually wins. To solve this mystery, we got a peek behind the curtain at how Haskell is really processing our code.
Which brings us to our first real clue: compiled code and deforestation.
To wrap our heads around why the interpreter is acting so strangely, we first need to look at the happy path. What happens when your Haskell code is fully compiled and optimized? Well, when you compile with GHC, the compiler doesn't just blindly translate your code into machine instructions. No, it's incredibly smart. GHC uses these things called rewrite rules. As Ang points out, there's a specific rewrite rule meant to optimize common list functions. The compiler basically scans your code, hunting for patterns. Specifically, it's looking for a good producer of a list paired right up with a good consumer of that same list. And when it finds that perfect match, it does something basically magical and eliminates the intermediate list entirely. It just rewrites your code so data flows straight from the producer to the consumer without ever building, storing, or trashing a temporary list in memory. That is a massive savings in processing time and memory allocation.
Now, what's really interesting is the terminology the community uses for this. In the programming world, this specific optimization technique is known as list fusion, or much more colorfully, deforestation. Makes sense, right? Lists in functional programming are often represented as tree-like data structures. So by eliminating those intermediate structures, you're literally cutting down the trees, hence deforestation. Ang notes that as long as you've got that good producer and good consumer, deforestation ensures the intermediate list just vanishes. It's an amazingly powerful optimization, but, and this is the vital piece of the whole puzzle, Ang makes it super clear that this deforestation optimization only kicks in for compiled, optimized code.
So let's look at part 2, the interpreter environment twist.
What exactly happens when we aren't running compiled, optimized code? Let's shift away from the compiler and into the GHC interpreter environment, because the rules of the game change entirely here. And this brilliantly illustrates the stark contrast between those two environments. On one hand, we've got our compiled code, happily using list fusion to optimize everything at compile time. But on the other hand, we have the interpreter. When Ang actually ran the benchmark in the interpreter, a completely different reality popped up. In the interpreter, there is zero deforestation optimization. The environment simply does not do it. Instead, the interpreter only does what's called desugaring with list comprehensions, basically just translating the syntactic sugar of the comprehension into simpler, foundational function calls. But it absolutely does not optimize away those intermediate lists. So, wait, if the interpreter isn't optimizing our list comprehension, how on earth is it still beating the manual fold in the benchmark?
Well, the secret sauce lies in the specific functions used inside that list comprehension. Ang points out that functions like sum and length aren't just your everyday run-of-the-mill functions, they are core primitives. Because things like adding numbers up or counting items are so fundamental to programming, the language designers heavily optimize these core primitives right under the hood. So even though the interpreter isn't doing the fancy deforestation trick, it is relying on these incredibly fast, pre-optimized core functions to do the heavy lifting. The list comprehension is essentially just acting as a clean, pretty wrapper around some highly tuned machine-level math.
Moving right along to part 3, the penalty of manual folds.
But hang on, isn't a manual fold also just doing math? Why doesn't that run just as fast? Let's zoom in on the exact performance penalties of a manual fold-L implementation to find the real culprit here. So, the crucial point is this. When you write a manual fold-L, you generally aren't using a pre-packaged core primitive. You're usually writing your own custom logic to tell the fold exactly how to accumulate the data. You do that using a user-defined lambda, an anonymous function. And according to Ang's notes, using fold-L with a user-defined lambda in the interpreter brings a surprisingly heavy performance penalty. Why? Because the interpreter has to continuously evaluate this dynamic closure application on the fly. It has to constantly manage and track the state of variables as it loops through the list step by step by step. Basically, the interpreter gets totally bogged down in the administrative overhead of managing your custom lambda function. Meanwhile, the list comprehension just hands the job off to the highly optimized sum or linked primitives. By trying to be clever and manual, you're actually creating way more work for the interpreter.
Let's bring this all together in Section 4, Readability meets Performance.
Okay, we have successfully solved the benchmark mystery. But what does this actually mean for you, the developer, next time you sit down at your keyboard? Let's see how this builds into a really solid, concrete best practice for your daily programming. Based on Ang's analysis, we have a super clear 3-step takeaway. Number 1, whenever possible, lean into using core primitives like sum or length inside your list comprehensions. Number 2, by doing that, you immediately get the benefit of vastly better code readability. List comprehensions are beautifully expressive, right? They're just so easy for our human brains to parse at a glance. And number 3, the absolute best part, you keep top performance regardless of your environment. If you compile the code, GHC's deforestation optimizes it perfectly, and if you run it in the interpreter, the core primitives keep things running lightning fast, completely dodging the heavy penalties of manual folds.
I actually want to read Ang's definitive conclusion directly from the source, because it perfectly captures everything we've talked about. Quote, using sum or length in list comprehensions is preferable due to better readability and no loss of performance. Honestly, this is the holy grail for programmers. So often, we're taught that we have to trade elegant, readable syntax for raw execution speed. We get tempted to over-engineer, to manually fold things, thinking we somehow know better than the system. But Ang's notes prove that, at least here, the clean, high-level code is actually the most efficient path forward.
Which brings us to our final thought for today's explainer. Now that you know the hidden mechanisms of list fusion, deforestation, and that heavy burden of dynamic closures in the interpreter, will you trust the compiler's primitives over your own manual folds in your next Haskell project? It's a really great question to ask yourself the next time you sit down to write a complex data accumulation function. Sometimes, leaning on the language's built-in optimizations doesn't just make your code beautiful to look at, it makes it wildly faster to run. Thanks so much for joining me to solve this benchmark mystery today. Keep learning, keep optimizing, and I'll catch you in the next explainer.